So I'm Stephen McQuistin. I'm a PhD student at the University of Glasgow, and this is work that I've done with my supervisor, Colin Perkins, and with Marwan Fayed at the University of Stirling. And what I'm going to talk about today is transport layer evolution. So how can we evolve the transport layer, introduce new protocols that better support existing and new applications? So what we want to be able to do as researchers and as protocol designers is to be able to build new and deployable transport layer protocols. But middleboxes in the network make this difficult. And so we need to learn about these middleboxes. We want to know what middleboxes are deployed in the network today and how these might interact with transport layer protocols. And that's why I'm here. So I want your help as operators, because you know what middleboxes are in your networks, or at least in theory you know what middleboxes are in your networks, and you know what they're doing. And so we want to talk to you guys, we want to find out about these middleboxes. So taking a step back then, sort of networking 101, we've got a layer diagram, the nice clean layer architecture, and we've got this notion of the end-to-end principle. And in theory then, we should be able to deploy our own transport layer protocols at the endpoints. As long as we keep the internet protocol layer the same, these two endpoints should be able to talk to each other over the internet, and that would be fine. But of course, that's in practice not the case. There's middleboxes in the network, there's NATs, there's firewalls, and all of these expect TCP or UDP. And they tend not to work when it's not TCP or UDP. So the transport layer instead looks something like that. It's TCP or UDP, and it's ossified around those two protocols. So we've got TCP and UDP. But unfortunately, these protocols aren't enough. TCP gives us ordered, reliable, congestion-controlled byte stream delivery. UDP gives us unordered, unreliable, uncongestion-controlled datagram delivery. But a lot of applications don't fit exactly with either one of these delivery models. So if it's a real-time multimedia application, for example, it might want the datagram delivery from UDP, but it will need some sort of congestion control, such as like TCP. So what's the solution to this? So what we propose to do is to use TCP and UDP as substrates, to essentially bring in a new transport layer above TCP and UDP and implement new transport layer protocols inside the payloads of these existing protocols. Now, a good example of this is Google's QUIC, so QUIC UDP internet connections, which gives some of the features of TCP, so it's connection-orientated, for example, but with a focus on removing some of the latency that TCP adds. So it has things like zero RTT connections, so it removes some of that latency. Now, unfortunately, UDP isn't available to all hosts, and by Google's numbers, it's around 5 to 10% of these QUIC connections fall back to regular TCP. Either UDP is rate limited to the point where it's slower than TCP would be, or it's entirely blocked behind enterprise firewalls. And so what we need is a solution for this that uses TCP as well. And that's the protocol that we're working on at the moment, TCP Hollywood. It uses TCP as a substrate, but again, it's designed to reduce latency. It does that in three ways. First of all, it's message-orientated to allow applications to send application data units. So if it's a video application, those would be frames of video, for example. And these messages are independently useful to the receiving application. And that property allows us to introduce unordered delivery. So messages are delivered to the application in the order they arrive. We don't reorder them because that would introduce latency. And finally, we make TCP Hollywood partially reliable. The application with its message will give us some sort of deadline, some sort of notion of when this data needs to have arrived by to be useful. And TCP Hollywood will estimate if that message will arrive by that deadline. And if it won't, it simply won't send it, even if it's transmitted it before. So just a quick look at the architecture of TCP Hollywood. Functionality is split across a user space intermediary layer and a set of extensions to the kernel. And this architecture allows us to have partial deployments. This intermediary layer can be used across both standard TCP and TCP Hollywood. So both endpoints need to have the TCP Hollywood intermediary layer, and they can talk TCP Hollywood. The kernel extensions are optional. Of course, you don't get all of the performance benefits if you don't have them, but both endpoints can still talk TCP Hollywood. So looking at how we implement messaging on top of standard TCP, we start off by disabling Nagel's algorithm. Nagel's algorithm batches up small TCP segments into larger TCP segments, and in so doing, it will introduce latency. So we switch it off for this application. So applications pass their messages down to the intermediary layer with some optional metadata. So again, a deadline and some dependency information. The intermediary layer will then encode the message to remove 0 bytes. We then use those 0 bytes as framing markers at the beginning and end of messages. What this lets us do is to delineate messages in TCP's byte stream. So if you can see the diagram at the bottom here, it's not sufficient to just put a message into a TCP segment, because there will be middle boxes in the network that resegment. And so we have these framing markers, and that allows us to see the messages. This process of encoding and framing is entirely transparent to the application. So the application can send and receive whatever data it wants to. And finally then, at the receiver, segments are passed up to the intermediary layer in the order that they arrive. And the intermediary layer can then decode the segment and pass any messages onto the application. It's important to note, though, that we acknowledge TCP segments as we would under standard TCP. We don't change that behavior. Looking then at partial reliability. So again, we have this notion of timeliness. So messages might expire, might not be able to arrive in time to be played out. We might estimate using an estimate of the round trip time that they're not going to arrive on time. And so they might expire. And under TCP Hollywood, these expired messages are not retransmitted. What we do instead is we find the next live message in the buffer, and we send that instead. And we use a mechanism known as inconsistent retransmissions. So we send the same length and TCP sequence number as we would under standard TCP, but what we do is we switch out the payload, and we send this live message instead. So that's just a quick look at TCP Hollywood. Just to make that more concrete, I've got an example. We're going to send some messages. They're going to be of a fixed size. We can see the buffers at the kernel, at the sender and receiver, and the user buffer at the receiver as well. And so we're just going to send these across the network. We copy it down to the kernel. It gets encoded and framed by the intermediary layer. We'll send it across the network. It arrives, gets copied into the kernel's buffer. It gets acknowledged as it would under standard TCP, and it gets copied out into the user's receive buffer. Now, because it's a multimedia application, we're going to have some notion of a playout delay. The playout delay will buffer until we've got 2 messages, and that's just to reduce any impact of jitter. So we'll wait for 2 messages before we start playing back this multimedia. So we'll send another message, this blue message. Again, it gets sent across the network, it arrives, and now we've got 2 messages in the user's receive buffer. So playout can begin. But of course, we're still sending messages, so we'll send this yellow message. It gets lost in the network, so it doesn't arrive. Playout, as you can see, is continuing. It's onto the blue message. But we'll send another message as well. So this red message, again, it arrives. It gets acknowledged as under standard TCP. We've got this missing segment, so we're acknowledging that missing segment. But instead of buffering it at the kernel buffer, what TCP Hollywood will do is it will copy it into the user space. It will make that data available to the receiving application. Because it's independently useful, there's no reason to buffer it. So we'll go ahead then and send another couple of messages, this purple message and the brown message. And by this point, we've sent 4 acknowledgements for this missing segment. And that will trigger a retransmission from the sender. So what TCP Hollywood will do is it will check the deadline of the message and an estimate of the round trip time, and it will estimate that the message isn't going to arrive on time to be played back. So what it will do now is that instead of resending this yellow message that was lost, it will find this pink message in its buffer and send it instead. But importantly, this retransmission has the same TCP sequence number and same length as it would under standard TCP. So in summary then, we still have this gap where we lost a segment, but we have that under standard TCP and TCP Hollywood. But we save these 2 segments. These would have been buffered in the receive buffer, waiting for this missing segment, and they would have missed their playout times themselves. So inconsistent retransmissions is visible on the wire. So any middle boxes that are comparing payloads with TCP sequence numbers would be able to see that we've done this, we're using this mechanism. They might interpret it as some sort of attack, a man-on-the-side attack, for example, and they might not like that. So we want to measure how deployable TCP Hollywood would be. So we conducted some experiments across most of the UK's major ISPs. What we did is we had TCP Hollywood connections running on port 80 and port 4001. We had some packet loss at the receiver so that we could induce some of these inconsistent retransmissions. Where we plot a green circle, the inconsistent retransmission made it through the network, made it back to the receiver. Where we see the orange triangle, however, the original data was delivered instead. So we saw a lot of split connection TCP caching on the cellular networks. And that's reasonable behavior. Most of the packet loss is going to happen not as a result of congestion. And this is a safe failure mode for TCP Hollywood. The framing and intermediary layer can deal with receiving the original data. It doesn't matter to the application. Of course, you don't get the performance benefit because the data has expired, but it is a safe failure mode for TCP Hollywood. From this data, then, we can say that TCP Hollywood is deployable. But then again, these measurements represented something like 14 paths through the network, and that's tiny. So what we take from that is that black box measurements are very limited. And measuring a larger set of paths is very challenging. And at least in this case, we needed to control both endpoints of the connection. We needed to control the client and the server. And that's difficult to scale. Further, these results give us only a snapshot. So these measurements were taken a couple of years ago, and the network will have changed perhaps significantly over that time. And inconsistent retransmissions are just one example of a wide variety of modifications to protocols that require middlebox support. So things like explicit congestion notification requires bits in the IP header, diffserv requires bits in the IP header, multipath TCP needs TCP options to work. And again, all of this requires middleboxes to cooperate either by not wiping TCP options or by setting bits in headers. So we need to measure all of these separately and perhaps together to see if there's any interactions between them. And that's where you guys come in. So we see how limited black box measurements are. But as I say, you as network operators know what middle boxes you've got. So what we're interested in finding out is what middle boxes are deployed in networks today and how those might impact innovation at the transport layer. So how do they interact with transport layer protocols? And sort of a broader, more conceptual architectural question is how do you as operators see transport protocols interacting with middle boxes? Should middle boxes be an explicit part of the communication between two endpoints? And having berated black box measurements, we're running a measurement study with a client that is publicly available, and we've got a server running at the university. The client sends TCP IP packets to the server. It will make changes to them, so it will set diffserv bits, it will set ECN bits. The server will then reflect back the TCP IP header it received, and the client will then be able to tell if something's changed along the path. Now, of course, the goal of this is to measure as many paths as we possibly can, so a diverse set of ISPs and locations. And that's, again, where you guys come in. There's a website if you can go to it and download the measurement client. Don't run it on the Wi-Fi network here, because that will be 300 sets of results for the same network. But bookmark it, download it, and go to your offices or homes and run it there. It will produce log files if you then just go back to the website and upload those log files, and we can analyze the results. So just in summary then, the specific question, I guess, from the talk is, are there middle boxes that you're aware of that aren't compatible with this inconsistent retransmissions mechanism within TCP Hollywood? And more broadly then, what sort of innovation do you think is possible given the middle boxes that are deployed in the network today? So please get in touch with us. I'll be around during the breaks, and my email address is up on the screen. And again, if you can download the measurement client software and run that on your networks, that would be ideal. Thank you.
Okay, there were a few people asking in the IRC room, do you think it would be useful if right patless probes could test TCP Hollywood capability?
It would certainly be useful. We've looked at it and we don't think it's possible that they would be able to, but we can look again.
Okay, I guess that's a RIPE NCC question to some extent. Okay, thank you, Stephen.
Thanks.
Any questions? Okay, great.